in Salem, we're going to talk about generators. And the type of generators that you find at the Salem and Hope Creek, those nuclear power plants, those are made out of what are called synchronous generators, which is what we're going to begin with our topic today. And so not by math, not by number, by sheer number, but by sheer size, synchronous generators are responsible for most of the power that we consume. It used to be almost all of it, not that long ago, but because of inverter-based generation and wind farms use what are called, mostly use what are called doubly fed induction generators, which we'll learn about induction machines in our next chapter. But the concept of a synchronous machine is that it works so well to support the grid, and you have this one additional control element that gives you so much flexibility and control that almost all the generation for many years was synchronous machines. And so if you remember when we determined the speed of operation of the Northfield Mountain hydroelectric facility, we said there was what, 48 poles, I believe. So the idea there is that that's a 48 pole generator. That's the number of poles on the stator and on the rotor. But the rotor itself uses what's called a synchronous generator design or a synchronous machine design. And we'll get into what a synchronous generator is. So the key thing is about all AC machines, the stator parts are always the same, regardless if it's an induction machine or a synchronous machine. They both have a three-phase set of windings distributed around the perimeter of the machine. The difference in a synchronous machine and an induction machine is what happens on the rotor circuit. And this is typical. You can actually swap the windings around, but for most applications, your rotor circuit's going to only be the difference. So you all own a synchronous generator. You all have one. Or might not have one.
Is it your car?
Yeah, it's alternator. So if you look back at some of the old school terminology, a DC motor or generator was not called a DC motor generator, it's called a dynamo. Full term, right? An alternator was because it alternated current. So a synchronous generator is an alternator. And in your car, unless you have like mine or you have a hybrid or something like that, you actually have an alternator, a three-phase AC machine that you don't know that it's three-phase AC because it immediately gets converted to DC to connect to your battery. But the idea is that you can go and buy an alternator from any shop. And if you have access to the individual windings, you can look inside and you can actually see the three-phase individual windings. And they use a permanent magnet, or no, they use a permanent magnet. It depends on the technology. Some use permanent magnets. Some people actually can control it. So you can actually have some voltage regulation control on it. And they actually can control the rotor field that goes in there. So like I said, large AC power networks rely almost entirely on synchronous generators. So Main Independence Station, which is just down the road in VZ, you know, what is it, 6 or 7 miles from campus? That's about 550 megawatts of rated output power, round boilerplate number or ballpark number. That consists of 3 generators. As we looked at, when we looked at some of those big generators and some of these nuclear power plants, 1,200 megawatts or so, those would all be synchronous. They're talking about building a solar farm in Bradley. That's another 7 miles from here. That's all going to be inverter-based generation. So that's where some of these newer projects are getting to be changed. I worked on a project over the summer that's going off the coast of Long Island, and that's supposed to be 1,200 megawatt of wind. And so they would use induction generators for that. So that might change a little bit as we get more and more into renewables, but we'll talk more about that as we get into the details. So how do you build a synchronous machine? Or a synchronous generator? We should be specific about generator because a motor and a generator is different. But the stator is exactly the same as what we covered last chapter, right? When we looked at those 3 windings, it's exactly the same. And then you have a rotating MMF or rotating magnetic field that when you add load to it, when you pull current out of it, you actually get that back EMF voltage that's generated. The difference is now we're looking at the rotor. And most of our synchronous generators will have a rotor that is excited by a DC voltage. And that's the key thing. Make sure you highlight it because it's very different from an induction machine to a synchronous machine, is the rotor. It's DC excited. You can use permanent magnet generators, which means you have a permanent magnet on the rotor circuit, but that's not always the best way to go because you lose one of those really important control capabilities of a synchronous generator. So the vast majority of them you'll actually provide the DC power to it. So how do you cool it? It depends. Most synchronous machines are air cooled, but the bigger ones actually use gas. And one of the ones that some of the big nuclear power plants they use hydrogen to cool the rotor. Anybody want to guess as to why they would use hydrogen? You mean its boiling point? You can run it a little bit colder, but you can run water, right? I mean, and there are some water-cooled generators. Not a lot of them, because water mixed with electricity is usually a bad idea. So if you spring a leak, you get problems. So a lot of times you like to use gas, and you still could use water cooling or air cooling on the stator part. But remember, we have this rotating part. So how do we keep that cool?
It's a no drag.
Yeah. Where does hydrogen end up on the periodic table? Number one, it's the lightest gas. It only has one electron in its valence shell. And so you have this big rotor, potentially really big rotor, that has to be cooled, but it's spinning at 1800 RPM, 3600 RPM. So if you have gas that is heavy, that creates a lot of friction and windage losses. So you'll use hydrogen on really large generators to cool it because you have just huge advantage for reducing your friction and windage losses. That's just on the rotating part. The stationary part, normally they just use air. They just run lots and lots of cool air because you can make it fairly large. So the generator that I spent a lot of time in, that was at Maine Yankee, was probably as long as this room. So what is that, 60 feet long and maybe 20 to 30 feet wide was the width of it. So you got to make them bigger because you have to have the windings, but more importantly, you also have to keep it cool because you do have I squared R losses in the machine. So keeping it cool is really an essential characteristic for making our generators work. Just like transformers. Some of the reason why transformers is as big as they are is because you have radiators on the outside and you need to be able to extract that heat out of the oil and dump it into the environment. Okay. So if you could run things at a cooler temperature, you could actually get by with smaller pieces of equipment. Is that viable to do? It's probably not worth it to have a room that's air conditioned to keep it at, 60 degrees or something like that. You can do that for an electrical server room where you have, 10 computers that maybe are putting out 10,000 BTU of heat. But if you're talking about something that is putting out, hundreds of thousands of BTUs, it's just not practical. So what you do is you just design it to run at a high ambient temperature. So most of your electrical equipment is designed to run at 40 degrees C ambient, which is 104 degrees Fahrenheit, roughly, I think. Ballpark. Do you know? Sorry, I don't mean to pick on you, but I'm assuming you're the only one who has degrees Celsius.
Yeah.
I think it's around 104 degrees. So it's designed to run at a high starting temperature. So if you run them at lower temperatures, you actually can get a little more out of them. And so that's really important to us in Maine because what happens in the winter in Maine? It gets cold. So you have all these pieces of equipment, right? Look around all these transmission lines that they're running in an ambient, let's say it's 40 degrees in the winter is the typical ambient temperature. Whereas in the summertime, it might be 90 degrees. So you can actually have separate ratings, and you have a winter rating and a summer rating so that in the winter, you can push equipment a lot harder without it being damaged. Sometimes 10% more than you do in the summertime. Already went through this one, right? The number of poles or pole pairs determines the synchronous speed. That's the rotational speed of that magnetic field. So that's going to operate that's going to dictate what our machine speed is. Because by the title of a synchronous generator, and we have something called synchronous speed, right? That's that magnetic field that rotates. The synchronous generator must operate in sync with the synchronous speed of the rotational field or the magnetic field. So this one has to run at 1800 RPM or 3600 RPM or 1200 RPM, et cetera, et cetera, et cetera. It cannot run outside those lines. If it does, it's not going to last very long. You're going to get a lot of vibration, et cetera, et cetera. So synchronous generators only run at that specific speed. Okay. Yes, sir.
Does it not just induce a current that's at a different frequency? If
No.
you're running at a different speed?
Nope. No. So if you remember from one of those slides we looked at the other day, we had two magnetic fields and we had this torque angle that was constant between them. So if this thing is spinning at 3600 RPM, and this is spinning at 3590, what ends up happening is this is going to slow down. That torque angle is going to increase. So what does that mean? It tries to put out more torque. So it's going to have more power going out until it gets to over here, then it slips a pole. It quickly very snaps around and then lines back up again, and then it starts to slip again. So it doesn't induce a different frequency. It's connected at 60 hertz. So you're stuck at whatever the grid frequency is. If it's running isochronously, so if you're running it independent from the grid, which is also called grid forming mode, if you don't care what the frequency is, it can be 59 hertz, 58 hertz, it will induce a different frequency, but we're talking about connecting to the grid. We're not going to be running in grid forming mode. Okay? That just causes lots of problems. The frequency of the electrical system in the United States is maintained under very tight tolerances. Moving by more than a tenth or a hundredth of a hertz is pretty rare. So voltage can change quite a bit. Frequency hardly ever changes. So these are locked in at that speed. And that's what another good thing about synchronous generators is they're designed to run at whatever whatever the equivalent frequency is that you have. We have two poles. We have a salient pole, which is for smaller, bigger turbines, physically bigger, not electrically bigger. And that's the concept where we have a bunch of poles. So we just basically take a sheet of steel and we stamp out the pattern that we want. And then that's made of, like I said, it's steel, so it's got some iron in it. And then we literally will tie them together, and then we'll use a rod that runs through them, and they'll hold them in place. We use laminations because, remember eddy currents? So we're really worried about eddy currents. So using a salient pole machine, you can reduce the eddy current. This is the size of a hydro generator, kind of big. You also see that here is our rotor circuit, and this is a how many pole machine? Can you tell by looking at it? 4 or 2? Let's count. 1, 2, 3, 4. So it has 4 poles or 2 pole pairs. So what synchronous speed would this machine want to operate at? 1800 RPM. That's at 60 hertz, not at 50 hertz. So one thing, and this is if you really get into graduate stuff where you're trying to understand rotating fields and all that stuff. We also have, we live in a stationary world, but sometimes we want to go ahead and put our axes on a rotational aspect. So in this case, we have to generate a set of new axes that rotate along with the rotor. So this direct axis or D axis is lined up with the north. And then we have a Q axis. Anybody here in the math, did a lot of math? Have you heard the term in quad or quadrature? That's a math term that means 90 degrees essentially. So it's 90 degrees ahead of it. And so we actually have one additional axis that we don't show here, but a lot of machine characteristics, we talked about direct and quadrature axis. So if I bring up this is from an older class or a different class. So So here is, this is up in Millinocket. This is for a small-ish hydroelectric facility. Small-ish, because you can see it's only 30.9 MVA. So that's not huge by any stretch. But if you look all the way down in the motor parameters, do you see anything relevant to what we just talked about for our rotating axes? I see some D's and Q's, right? So the way you model machines in a lot of cases is you use these D's and Q's to show what those parameters represent. Okay, so you can actually have the ability to measure D's and Q's. We won't get into that level of specificity for this class, but you're actually able to understand where those terms come from. So that's the direct and quadrature axis that we see in any rotating machine. Here's a picture I took. This was at AC Electric down in Bangor. So if you get off on 395, there's a facility there that they can actually go and build or rewind, I should say, synchronous machines or induction machines. And you can see, if you look closely, it's kind of rusted out a little bit, but you can see some lines like this. Those are the laminations that we have that's shown there. And then look at the windings. You can see the windings that run in between those poles. So this is a smallish synchronous, this is the rotor circuit of it. What is this over here? What's that? It's a fan, yeah, it's fan blades. So as this thing is rotated, it's driving air over the rotating part of the machine to help get that work. Anybody know what this is? Bonus points? No, this is all rotating on the shaft. What's that? Close. This is the actual part. You actually can't see the brushes. What's that? Nope, this is actually another generator. This is what's called a pilot exciter. So it gets its excitation from the field through here. And there, you can't see it here, but there's another way to convey energy to get the DC out of it. So this is actually DC. And over here, if you look really closely, anybody want to guess as to what those are? I'll give you a hint. If you're an EET, John Allen will be very disappointed at you. If you're an ECE, Nuri Imantologu will be very disappointed at you. For semiconductors, they're diodes. Those are diodes.
Oh, yeah.
You need DC, right? So you only have two wires go there. So you get the rectifier bridge and you actually build it onto the end of that rotating part. Because this is generating AC, right? We know that it's going to be spinning around. So we know it's got some AC. You got to convert that to DC. And how do you do that? That's something spinning. You just tack on some diodes. All you need to do. So this one gets its own self-excited. It actually gets its own power from its little pilot exciter that lives right on the end of the shaft. Not always the most common. Some of them use a different design where they'll get power separately from a different location. But I can't remember the application of this one, but this is how they worked it. Yeah.
On the laminated next to the diode, those was more rectangle 9.
Right here?
No, on top against your left.
Right here?
Yeah, those ones. How many do they? What is the ratio if you have 4 pole and how many of those? What do you need?
Ah, good question. What's the ratio? And the answer is it depends on the speed of operation, right? So the number of poles that you're going to have here, this one might be a little easier to figure out because you have these big windings. But over here, all I need to do is get DC out. So why do I care what the frequency is? It could be 10 million hertz, right? It's immediately going to get converted to DC. So this one, it looks like there are lots and lots of windings that go through there. But the reality of it is, it's whatever it needs to be for the diodes to be happy. So I don't know. And you can't tell because if you look closely, let me erase a little bit. You got to really look closely, but some of these windings, it looks like this one goes over here. So that's the same current, that's the same phase current. So that could be another pole pair, or it could just be distributing the winding on the perimeter of that shaft. So you can't tell by looking at that. One other thing that's interesting, look at this is, remember that's copper wire, right? Why does it look purple? It's magnet wire. So you buy wire, it's the insulation, and magnet wire has that purple covering. So if you go buy magnet wire, boy, I still have this up. Oop. So magnet wire. Kind of purpley red. I don't know if you can see that, because it has a very thin insulation coat on it. I can't imagine that this is magnet wire because it looks like it's pure copper. But it says it's enameled, so maybe they're using a different type of insulation. But all the magnet wire I've ever seen is purple. And it's just because when they pull it through a solution that bonds the copper, and that's where you get the insulation. Because remember, in here, hopefully you can see it, but you certainly don't want this copper wire to connect to the adjacent one, because why would it go through the motor? We're just short out. So you have to have that insulation between there to keep that going. Anybody know what the tape is for? Or it could not be tape, it could be like a cloth.
Keep the line straight.
Yeah, basically keep them in position, because most likely you may have some spacers or separators in here, depending on the voltage, that keeps it from moving. And if you have this thing spinning along, you don't want those windings moving relative to each other. It would vibrate. What would happen with vibration over time? You would have friction and you'd wear down the insulation, so you get short. So what you need to do is you need to make sure that that's very well secured inside there. And so in this case, they just use this cloth or whatever to kind of hold it in place. But this was all hand wound, believe it or not. Cylindrical is basically you take a piece of iron and you literally mill out the channels for where you want to put the wire. So this is just a big piece of iron. And then you can see I've milled out those areas. All right. This is for high speed applications and generally fairly high power. And the reason being is to make something like this that can spin at 3,600 RPM needs to be pretty heavy duty, pretty beefy. That's a lot of centrifugal force. Over here, it's a solid piece of iron. So the iron itself is not going to fall apart as long as it's well made. They do have to wedge these in. So what happens is, this is how it's shown. In reality, the way that they're typically milled out. So here's the shaft, here's the opening, and then you kind of do this trapezoidal image like that. And so you'll have windings in here, and then you use a wedge that you drive in that holds it in place. And that's how those are designed to keep it to stay in. Like I said, 3,600 RPM, but you can go down 1,800 RPM. Most of them are 3,600 RPM, but again, 1,800 RPM works fine. You can use the conductor cooling, air, water, or hydrogen. I haven't ever seen any water-cooled ones, but they do exist. Most of them are air. Really big ones are hydrogen. You can get up to 2,000 MVA, although I'll be frank, I've never seen a 2,000 MVA. The biggest one I've ever seen is 1,500. 2,000 MVA, there's some real problems with that. First off, just the amount of power, the amount of mechanical power you need to drive it. I mean, a nuclear power plant might be able to push 1,500 MVA. It's a very big power source, a very, very big reactor. And to get to 2,000 megawatts or 2,000 MVA, you just would need such a massive source of power. It just probably isn't practical. Some of the big nuclear reactors in Russia, they use that, but they can't even use the designs in the United States, because the reactor designs we use are cooled with water. And in Russia, they use graphite. So they just have big reactors and they have to just get so much heat pulled away from the reactor. It's not possible without a lot of water. So they just use graphite, and basically it's a heat sink. It just makes the area of the reactor bigger. So I've never seen anything 2,000. 1,500 is the biggest one I've ever seen. D and Q axis, just like we saw before, you can see you got stator windings, an air gap, rotor, and rotor windings. Here is the stator. I don't know if you can tell colors, but you can kind of see the green here. That is the stator for where this rotor assembly slides in. That stator is just like any old stator. And you can see how, and Barzilai asked the question about the wires, you can see how they wrap around, they go through, and then they wrap around and come back. That's the stator winding. Just whatever the number of poles on the rotor has the same number of poles on the generator, on the stator part. So they would have to figure out, how to wire that in the back. But essentially, that's the stator. It's the simplest piece of equipment to make. You do have additional stuff because this has got to sit inside there. How does it sit inside there? You got to put bearings at the end. So you actually have to have this shaft sits on the ground. But what you do is you slide this unit in very carefully because you don't want to damage the windings. And sometimes the air gap is 20 millimeters, very, very tight gaps. So you got to slide it in very carefully. And then at the end, you have to mount it to a support for the actual rotating part. So alignment is really crucial. So however you pour the foundation and you get all the metal, you got to make sure. So a lot of times they'll actually have a frame, a metal frame that is manufactured at the facility, and that'll actually make sure that everything is perfectly straight and aligned and all that stuff. So you actually need a pillow, like I think they call it a pillow bearing or a pillow block. That's just old terminology that they use. Because what do you do at night? You rest your head on the pillow. So you're resting the shaft on a pillow. So that's why they'll call it pillow block to support it. And that's on the end. Nothing is supporting it on the inside. So you can see why, look at the shaft of this one. Look at the size of that. Why is it so big? Because it has to run all the way from here to here without coming into contact with the generator. It has to be up in the air. It has to be suspended. So you just have to have a really difficult or strong piece of mechanical system to go ahead and support that way. Yes, ma'am. No. No, good question. So would they be insulated SF6? What is SF6? Sulfur hexafluoride. It's a really good insulator, but it's actually really bad for the environment. So they're getting away from sulfur hexafluoride. So SF6 is usually only for voltages above 35,000 volts. They're just insulated with magnet wire, and each turn of winding only has a volt or two difference between it. So you don't need that level. It's only when you go out into the transmission system where you actually step the generator voltage up, which, as I said, they're never higher than 25 kV, which you can do that with air or other things. You usually vacuum, depending on what it is, but then you go up and you go into the higher voltages. So the insulation, and actually the insulation, hardly ever even see SF6 insulation. Inside the breakers, they have little bottles of gas, and that's where they would interrupt the fault in the SF6 because it's very quickly extinguishes the arc. You can use air, but the problem with air is it's not clean and you can set up ionizing paths. So your breakers would be really big. So anybody know what they used to use for breakers before SF6 was around? Oil. Oil is great, right? You can have oil that has the right elements added to it, makes it a really good insulator. So you'd use oil-filled breakers. The problem with oil is it just became impractical. If they didn't have really good flame retardant oil at the time, so you get fires. So they did use air as much as they could, but they did use oil for some of the high voltage breakers. And then they switched over to vacuum breakers. So how does electricity travel in a vacuum? It can't. There's nothing for it to travel through, right? But you can't get to a true vacuum. You can only get to a kind of a vacuum, because a true vacuum, you have to have a really beefy piece of equipment. So with vacuum, that usually is limited to anything under 35,000 volts. Although they're starting to get better with some of the technology, and they're using different gases. So usually we'll see SF6 only at 35 kV and above. Sometimes on big generators, because if you have a big generator circuit breaker, if it's pulling 10,000 amps, you just physically need a lot of room. So sometimes they use SF6 because they don't want the breaker to be the size of a house. So they might use that, but SF6 is pretty limited for that. One of the other things too about these rotors, are really long. What happens when you suspend something over here and over here and it's really long? It,
Say.
or bows. So they actually have these things in big generators. It's called turning gear. And it just sits there and spins the unit at a really slow speed. And the whole reason why it not spins, it rotates it, is to make sure that the turbine, the thing doesn't bow. If you've been shut down for a long period of time, you're gonna have some bow in your turbine. So then you gotta spend the next however long, you gotta heat the unit up and then you gotta slowly rotate it until it gets to the point where there's no vibration and there's no bow in it. So long ones like this can be a real problem. That's the other reason why you don't want too big of a generator, because the control and maintenance of it is just, it's just becomes a lot. Who had their hand first? I didn't see, I'm sorry.
All right, if you tipped your generator up, would you avoid that problem? It was,
Excellent question. So the generator's like this. Do you want to do it like this? Why not?
The starts one might rotate.
No, you could support it. You could have another member like this that would support it this way.
Gravity will pull down on the road.
Okay, so say more. Say more about that.
You have more pressure. The road is pulling, going down more.
You always have gravity pulling down. Remember, that has to spin. So you need a really beefy bearing. You'd have a lot of friction and you need a bearing that would be absolutely massive. So it just wouldn't be practical to have something that is like this. That's why they do have something called vertical axis wind turbines. With that same concept, they're thinking, oh, well, we'll put all the weight at the bottom, and then we won't have all the weight at the top of the tower. The problem is that weight is all sitting there on that bearing, and you need a really heavy duty bearing to do that, needing a lot of maintenance. So from a mechanical perspective, it's not practical. Electrically, it would work fine. And there is something that talk about magnetically levitated bearings that you could actually magnetically levitate it. But the thing is, just think about the weight. I mean, this is massive weight. You need a lot of magnetic field, and inside the machine itself are magnetic fields. So now they're starting to interact with each other. Are they going to give you the performance you expect out of your machine? It becomes an issue. So I don't think I've ever seen, except for hydroelectric facilities, where all those hydroelectric facilities, those are going down like this just because of the design, the way they work. So they have to go down to the impeller where the water is spinning. But those are generally hydroelectric ones are pretty small. They do have the ones at Hoover Dam and China. There's a river in China, but I'm not even sure if those are vertical axis or not. I've never seen them, but hydroelectric ones, like the one that I showed you the picture for Northfield Mountain, those were vertical axis ones, but very uncommon.
that's what I was thinking of, that's why.
Yep. But if you remember the shaft size of those things are monsters, right? So a shaft size like this could be good for 300 MVA, but if you spin it at, 3,600 RPM, that same shaft size could do 2,000 megawatts. So it just would be a lighter one for a much bigger application. And then again, you need that long length. So it's got to be standing in here. Now you got to go ahead and erect something that goes straight up and won't move around. So we have to build this. It has to be practical. So it makes it challenging.
For the big one, right? Because you said that when if you stop it for a long time, you're gonna run a little bit. Now, do they spinning even when it stops at the lower speed?
Say that again?
Do they leave it spinning even when they want to stop it? Is it practical to leave it spin for them to?
If it's going to be shut down for an extended period of time, so the bow won't happen right off. It just takes time, right? Gravity has to do its work. So it just has to take time. So they have a certain amount of time before they have to get it to spin. So if you have to shut down for maintenance, and I don't know, it depends on the metallurgy of the machine. The manufacturer will tell you if you're going to be shut down for more than, let's say, 5 days, you've got to get it rotating. Otherwise, the rotor bow inside the generator shaft could actually impinge upon the windings inside the stator windings inside the generator. So you'd have to get it rotating, or you're going to have to take the unit and jack it up and do all kinds of different things. Because that air gap is going to be tight. You don't want a big air gap. So it's not like you can just have a variable air gap. It should always be as small as possible.
So they can only shut it down for the lines.
Yep, and then you got to talk to the metallurgist. It's part of the length and all this stuff. I mean, you don't really, to the best of my knowledge, they don't really strengthen rotors, especially these round rotor ones. These are the long ones. They just make them with iron, and then I don't think they'd put other metals in there. I don't think so. No. So for a generator, We need mechanical power, which means we need a prime mover. And that prime mover could be anything. Could be a hydroelectric turbine. It could be a steam turbine. It could be a reciprocating engine. It could be you riding on your bicycle as fast as you can. Mechanical energy, right? Doesn't need to be anything other than that. So I need a prime mover. Now I've got to have a DC current flowing into that rotor winding. It's going to produce a magnetic field that lives on the rotor. That rotating magnetic field is living inside of windings. And remember that K feed ET that we had, it's always going to introduce a current. So as I rotate inside those windings, I've got generator action and it's going to cause a current to flow. And it flows inside the stator winding. This equation should look familiar to you. This equation we developed last chapter, which is what is our electrical frequency? How does it go? Number of poles divided by the synchronous speed or mechanical speed, because it's a synchronous machine, they're the same, divided by 120. We live in 60 hertz land. That's why we said 3,600 RPM, 1,800 RPM, et cetera, because this is always going to be equal to 60 hertz. One thing to note, this is the electrical frequency on the stator. So interestingly enough, with an AC machine, we have two separate circuits, right? We have a rotating circuit that's fed DC, and we have a stationary one with 3 phases, and this is AC. So we have two completely independent circuits from each other. So if we want to analyze these with circuit analysis, we have to analyze the DC circuit separately from the AC circuit. Because what gets induced over here is a magnetic field, and that's what creates the windings. So we electrically analyze the circuit over here, and it's DC, which flows a current, but then we get some way of calculating what the magnetic field is going to be, and then that rotating magnetic field in the stator winding is going to drive a current. So what you're going to start to see now are two separate circuits, kind of like in a transformer, right? Here's the primary winding, here's the secondary winding. Are those having any influence on each other? If I've got a ground over here and I put a ground over here, does anything happen? They're electrically isolated from each other, aren't they? So the analysis for this part can be done somewhat independently on this part, except we know that the current over here is related to the current over here. That's not the case over here. The current that goes into the DC circuit is somewhat independent, or 100% independent from the AC. How about the current in the AC? What determines the current in the AC? Sort of. How about the load? If I get a voltage and I put a load on it, isn't that what Ohm's law tells me? The current is going to be I equals V divided by R. So the current through here is going to be determined by the load, but it's also determined by the voltage. And that's where this DC current actually has control. It controls the voltage on there because, is it on the slide? Yeah, next slide. My back EMF voltage, that voltage that lives across that stator winding, that generated voltage is equal to some machine constant times phi, which is magnetic flux, times my frequency. So that's how I generate actual voltage. That's the only relationship that the two have between each other. Okay? And since this is magnetic material, and it's no big deal to operate things way over magnetically, we can just go ahead and we can look at or come up with a plot that shows that if I have a field current, remember this is DC, that's going to create a back EMF voltage. This is an AC voltage over here. That's the voltage that is across those windings. So I can look and see if I drive so much field current, Here's what the voltage, now this is internal to the machine. This is across the windings. It actually isn't the terminal of the machine. So inside the machine, I generate a voltage. The terminal of the machine can have a different voltage because the windings itself are going to cause voltage drops, and we'll see that in a minute. But to actually determine what that internal voltage is, we just have to look at this curve. So drive field current, you get a voltage. If we go back to, oh, go ahead, Barzilli.
The E then is AC.
The E is an AC voltage, yeah, because that's on the stator winding. That's what connects to the grid. So that's an AC voltage because it's rotating that magnetic field, which is constant, right? Because the DC source, it's rotating with inside winding. So sometimes it's perfectly aligned, sometimes it's 90 degrees out of phase, and you're going to get a rotational voltage that way.
And then how is it connected? How is it related to the DC on the circuit?
This right here,
Yeah.
right here. This flux right here is because of the amount of field current. The more DC current you have, the more flux you're going to get in that rotor circuit, which is going to allow you to control the voltage. So if I go to here, I didn't show you these yet, I don't believe. Look at all these curves. Loads and loads of curves. This plot has a lot of information on it. It's kind of clever how they did it, but if you look closely here, what does this say? That is equivalent to my field current. This is plotting DC current on the x-axis. And then if you look over here, we get an output voltage. That no load voltage curve is the back EMF voltage when we have no load on the machine. That's the actual voltage that's created on the stator one. So this curve that does this, that is this curve right here. It's the same curve. And it shows you saturation. This is a real world machine, right? This is not something I made up. This is something that I think this was ABB. They came up with this curve. And you'll notice that field current or excitation current is the x-axis. Why is that? Remember the concept of curves, right? Curves have an x-axis and a y-axis, two-dimensional. The x-axis is the independent variable, and the y-axis is the dependent variable. So you can see here, this voltage here, this E that we get, that is exclusively determined by the field current, especially, or I should say, particularly when it's running at whatever the synchronous speed is. That's the voltage you're going to get. And since this machine needs to operate at synchronous speed, that is completely determined by the field current. This voltage has absolutely no impact on that field current. You're literally driving that. And if you look at old school pictures of people working at synchronous at the generators, you'd literally see a person standing in front of a big resistor with a handle, and they would rotate the handle based on what was happening in the grid. So all these hydroelectric facilities, before they automated them, they used to have, literally they had staff 24/7, and one of those people was responsible for turning the rheostat inside those. I wonder if there's a picture. The grid's got everything, so let's see. I might need to go to Google.
And that resistor would adjust the DC of the.
It would adjust it, either increase it or decrease it. So you have a fixed DC source over here, and you could do that. Back in the day, it was a lot harder because they didn't have semiconductors with a diode to do it. There were ways to do it with swapping poles, but it was much, much harder to do than it is today. Today, we saw that those diode packages. So let's see. Old photo of staff turning. Let me see. I remember seeing a picture of somebody standing. Outside or in front of. That one I can't tell. Let me try a hydroelectric one. Because those ones were a lot safer. That's cleaning it. I mean, these are old pictures. You don't see, I guess you can't find anything, but. Yeah, you can't really see them. Sorry. But I remember seeing a picture a long time ago on a book where somebody was literally just adjusting it. So that's what you're doing over here.
So the idea is to adjust the resistance.
You are adjusting the resistance, but the voltage here. So essentially what you're doing is you have a DC source here, and then you have a variable resistor. So you're increasing or decreasing that resistance to increase or decrease the current. And so they would have somebody on staff that would sit there and monitor the output voltage, and they would sit there and adjust if the voltage was too high or too low.
But if the output voltage is too high or too low, like adjust the resistance here.
Right. Because of the voltage, let's say over here, that's way above nameplate. What do they need to do? They need to bring the current back down and make it so that it was a more manageable voltage.
But then now everything is electronic.
Everything's automatic.
Automatic.
Yeah. Everything is done with electronic, diodes, and they will have a computer. There's a company called Basler Electric that they make these solid state voltage regulators. They're one of the big ones that make it. And then also all the big generator manufacturers, they make their own as well. But they're all done automatically. They've been doing them automatically since probably the 60s, maybe even the 50s. But 100 years ago, they were all doing it by hand.
Because I remember something close like this, but then it was more of the output voltage, the voltage which come out, you step it down a little bit and then you supply it.
Well, this is going to be equivalent to the output voltage, not exactly the same, but it's
Yeah.
equivalent. So if you decrease it, you'll be able to decrease the voltage. What we're going to learn with synchronous generators is that we actually are monkeying with that. We're actually not changing the output voltage. We're changing something else. We'll have to look at phasor diagrams for that. So nowadays, the voltage on most generator outputs, you can't change them all that much, maybe a little bit, but not that much. But you can change the reactive power output. And that's what more people are watching now, is what's going on with the reactive power. As long as the voltage is within reason, they don't really change the voltage. It's more of the reactive power. We'll have to get into phasor diagrams to do that. We're not quite there yet. We'll get there. So voltage regulation, same exact equation. So depending on how tight you want to maintain your tolerance, you're going to go ahead and look at voltage regulation. Keep in mind that voltage regulation, though, is only based on, it's not really a typically usable number unless you've got a lot of load. So this is a way of telling you what your synchronous reactance is of your generator. Okay. And those, if you remember from here, let's see, where's the, put it, close it. Huh. I didn't think I had closed the, oh, here it is. So over here, if you look at these values, 0.75, those are in per unit, they'll make more sense to you, but you typically would want those to be as small as possible, typically. So I won't get into too much other than to say that the voltage regulation, it really depends on power factor. If you have a lagging power factor, your voltage regulation is hard positive. If you have a leading power factor, your voltage regulation is negative. Why is that? When we talk about a lagging power factor, let's draw a power triangle. Here's V, here's I, and then let me actually do it over here. So here's V, I, here's my lag. And if I do my power triangle, I have this, right? Q is positive, So in the case of a generator, right? Here's my generator. P is always out. In the case of a lagging power factor, Q is out as well, right? In a leading power factor, Q is negative. So now Q is in. So this means under a lagging power factor, all the reactive power that the system is needed is coming from your generator. Over here, you've got excess reactive power factor in your system, so that actually has to go back into the generator. So this is a case called overexcited, and this is underexcited. So most generators operate overexcited. That's what they're tended to operate at, but they have the ability to operate underexcited. Remember the curve that we had here? Let's look at the snow cone. Do I not have it here? Here we go. Look at this. Overexcited, underexcited. The generators can operate in either direction. Within reason, you can see at 0.95, lagging or leading, they're, they have that nice round shape. Once you get beyond there, you can start to see that they tail off pretty rapidly. So most generators can operate at plus or minus 0.95 power factor and still put full output. Once you start getting beyond those, all bets are off. And the determination of the power factor is what does the grid need for power factor support? Does it need reactive power or does it need to absorb reactive power? Most generators are going to be operating over here, unless it's at night and there's all kinds of wacky things happening. You get a sense of here. So I understand why they do this here, but to me, I would rather see this as, instead of under and over, I'd rather see it as leading and lagging. Because that's actually what's happening for a power factor. Overexcited means you're putting more DC energy that's necessary to support the magnetic field of the generator. So that extra magnetic energy you put in is actually helping to provide reactive power. Underexcited means you're putting in not enough DC power to maintain the magnetic fields inside the generator. So the magnetic field support actually comes from the grid. That's why they call it over and underexcited. That's where those terms come from. All right, so let's build our equivalent circuit. And you can take a look at a lot of information in here. That's not really relevant to us unless you want to really understand what's happening inside the physical machine and what's going on. This is what's important to us. Remember, electrical engineers, we love modeling. All engineers love to model things. It's too hard to look at a hunk of iron with windings and all that stuff and figure out how it operates. So we're going to build an equivalent circuit. That's our model that we have, and then we can analyze that. So I've got a couple of inductors. Normally we'll combine these. And I have a resistor. If it's a generator, my armature current is going out. If it's a motor, my current's going in. So a synchronous machine has the exact same equivalent circuit. It's just the current direction is different. This voltage over here, you see EF, but you said you can give me a hard time, say, hey, Paul, you told us earlier that the EF is determined by that saturation characteristic, right? Didn't I tell you that? So why don't I include that here? Well, I kind of would. But this is the DC circuit. This has nothing to do with the AC circuit over here. So from an equivalent circuits perspective, if we really want to analyze it, all I can do is analyze it from here. And somehow I need to look at that curve to actually get my value EF. Again, you do the same thing in electronics, right? When you use small signal analysis, you have this bias current that sets up, how what the amplification is going to be. And then you can go ahead and look at the curve and come up with some reasonable points. You're doing the same thing over here. Okay. So you have X, leakage, XL is the leakage reactance. You have RA, which is our armature reactance. So resistance. So you have coil of wire, it means you got some resistance. And then you have your terminal voltage here, which again is very different than that back EMF voltage because all of these are going to cause a voltage drop. That's why I said when we looked at the Northfield mountain generator, I said that was the no load or the open circuit characteristic. No load is open circuit. It's the same thing. So the concept here is that those would be the same. VT and EF are the same only if there's no load. But there's always going to be a load. We're not going to run a generator with no load. It doesn't make sense to. We need to make money on it. So this voltage should always be different than EF. It could be greater in magnitude, or it could be less in magnitude. And that depends if it's over or under excited.
What did that say at the bottom? Combines to form X1.
Synchronous reactance, X sub S. So here's our phasor diagram. Lot happening here. We'll focus on this stuff later because that's those magnetic fields and what's happening in the magnetic field. What's way more interesting is what we see to the right over here. By the way, can you tell me if the circuit is leading or lagging power factor, or is there not enough information to tell?
Looks like it.
Yes, what?
It's lagging.
Why is it lagging? VT is left than EF? What's our concept of leading or lagging? Who leads or lags whom? The current leads or lags the voltage. If I look over here, here's my voltage. I can measure this voltage, can't I? I can walk up to the terminals of the generator and measure that voltage. I can't measure this voltage. It's inside the machine. So I can pick this at an angle of 0. The current is coming out over here. So this is a lagging power factor because the current lags the voltage. And you can see when I do that, when I lag, I've got a voltage drop across the resistor that's going to be in phase with the current. And then I've got a 90-degree phase shift for that voltage drop across the leakage reactance. And I have another voltage drop across that other X value, that armature reactance, that is going to be 90 degrees out of phase. And this is the magnitude of the voltage that I need to do to be able to get a terminal voltage that's rated. Okay. I have a delta here. This is the angle between EF and VT, which happens to be the same angle as over here. Do you remember what I called that angle when we looked at this in machines earlier? We looked at the end of last chapter. What do we call that angle? The torque angle. So this delta actually tells you how much power this machine is outputting. So that is equivalent. So there's a couple things happening over here. If you look at the magnitude of VT, so what I do is I will draw a circle. Here's the magnitude of VT. Here's the magnitude, if I could draw correctly, of EF. You can see that the magnitude of EF is much, much greater than VT. That's always going to be the case for a lagging power factor. How about a leading one? Where's my whiteboard? Oh, where's whiteboard? Is it close? I had a lot of problems with whiteboard earlier this morning, so. So we just did a lagging. Let's do a leading. Help me out. My brain has turned to mush. All I know, here's what VT is. Can you help me draw a leading power factor? Like that?
Yeah.
Now, let's put IARA like that. And let's just combine those two reactances. So this is my IARA. And normally you can neglect it because this is usually much higher. This is the EF. Look at that magnitude, if I could draw correctly. That magnitude is greater than that magnitude. So when you operate at a leading power factor, your internal voltage has a lower magnitude than your terminal voltage.
Which means you giving up low voltage than what we had in the beginning of the.
I don't know what you mean by giving out more voltage. Can you explain? I'm not trying to argue, I just didn't understand what you meant.
VT kind of the output voltage and then.
The output voltage is higher than the input internal voltage.
The internal voltage. Which
Yeah.
is a good thing or bad.
It's fine. It's neither good nor bad. It is what it needs to be. And as we mentioned, your internal voltage is not high enough to maintain excitation to deliver terminal voltage. So it's stealing some of the magnetic energy from the field, from whatever's connected to it out in the world, to create some of that magnetic energy that's necessary to maintain the system. So it should be less than VT. And that's why it's called underexcited. The magnitude of EA is less than the magnitude of VT. It's not, the field current that you need is not enough to deliver terminal voltage by itself, rated terminal voltage. You've got to steal some reactive power from the grid to be able to do that. Where if it's overexcited, the voltage is much higher than it needs to be, or maybe a little bit higher than it needs to be to maintain the terminal voltage at nominal, around nominal.
That's a good question, right?
Yes,
On this graph, there's no, the DC current is not on the graph. There's no. Okay.
wasn't in here either, was it?
Yeah.
The DC current helps to dictate these, which in turn dictates that, but that's it. It's not a direct connection. It's just magnetic fields. And just like in transformers, they're electrically isolated, so we don't show them.
And then also, what will cause the power factor to be leading?
Excellent question. What causes the power factor to be leading or lagging?
The inductor.
What's that?
The inductor inside? might
No,
cause-
the inductor doesn't change.
That's the load.
It's whatever connected to the load. So if the load says, hey, I have to run at a 0.9 leading power factor, if you want to connect that grid and operate the grid within range, you better have that generator able to take in enough to maintain that 0.9 leading power factor. It's always a load. Remember in this class at the beginning, what did I say rules the roost? The load, right? So you can even see it here. The generator has to be capable of adjusting itself up or down. The load can adjust itself up or down, but why would you want to adjust the load? I want to offer to you as much as you're willing to take. Why? I'm not doing this for free. You're going to take this out of my hand, and then your other hand, I'm going to be reaching in your pocket and grabbing your money, right? That's what the utility bill company does. They send you a bill. So I'll give you as much as you can take, as long as my system's not going to fall apart, and you're going to compensate me for that. So I only get paid because you have load. I'm never going to restrict your load unless, like, you know, it's the heat of summer and, you know, there's no reservoir with water or something like that, where, you know, you're in California or Texas. Remember a few years ago in Texas, they had massive problems. At that point, they did shut down parts of Houston and all that stuff because they said, we just can't keep the grid going. So at that point, they said, kick customers off. So not only did the state of Texas have some major problems with it, but the federal government had problems with it. And now all the consumers were all upset too, because now they're like, well, why is the grid reliable? Why did it pay you? So the utility never wants to be, you know, the bad person saying we can't support the load. Very bad. Plus, it really affects your bottom line. So not a place you want to be. Three-phase machine means we have three separate windings that are completely independent of each other until they're connected internally or externally. If you were to buy a generator and look at the connections, first time I saw this blew my mind. That's what I saw for a connection diagram. It's like, what the heck is that? Why does that exist? Why do I have 6 wires coming out of the generator? Because you have 3 separate phases, and it's only when you connect them together that you show the connections. So every real world generator, this is called an AC elementary or a 3-line diagram. If you want to learn more about elementaries and stuff, you can take my 423 class. But these AC elementaries actually show how things are connected. And that actually shows you all three windings, because a lot of times you're monitoring these to be able to tell the health of the generator.
So would that be a Y connected generator? Do you still call them Y or delta?
Yep. Still a Y connected one. This one, it's not grounded necessarily, but it would be. But every generator is going to be connected in a Y or delta as well. Most generators, you would connect them in a Y, and you would ground the neutral, maybe not a solid ground as I've shown here, but you would ground it through something. And there are major reasons why. That's more of a protection discussion that we have, but you would certainly ground them now. And look at that. V line to line, square root of 3 times the terminal voltage. Exactly what we'd expect it to be. So now you actually see with a 3-phase, all that stuff still holds true. If it's a balanced system, the square root of 3s and the 120 degrees, all that stuff is still applicable because the generators are being built to produce exactly this. It's all just a balanced system. How to do for time? Not too bad. I was worried this class was going to be too short, but I guess I got rambling. I can show you, let me see if I have it here. This is another generator. I'm not sure if I have it in here. Let me just double check. This is another pump storage facility in Massachusetts. Let's see. No, I don't want that one. I might not have the drawing. Yeah, so remember I talked about an AC elementary? Wow, you guys are getting a lot of bang for your buck today, getting all these real world drawings. This is an AC elementary. This is the actual how that you connect it. Scary. What do you think you're gonna be doing this summer?
It's probably like day one. Yeah.
Day one,
Or you might be up one.
10-minute, right? First 10 minutes you're gonna be doing this stuff.
Oh my.
Look at that. I don't lie. Honest Abe here. This is a generator. This is a 333 kVA, 415 horsepower, 415,000 horsepower. It's the same thing. It's pump storage. So you can either pump water or you can generate electricity. So these are a little bit bigger units. Here are the terminals, and look in here. This is the neutral connection. How do I know it's the neutral? This actually connects through a transformer. And what do you see right here? Ground. This is the neutral point. All three wires go to that same point. So this is how it's grounded. So this is a Y connected generator that actually has a bunch of current transformers in the neutral winding, so you can monitor it. So the actual generator is shipped with 6 wires coming out of it. You've got to connect it in any manner that you need to. And like I said, this is Bear Swamp in Row, Massachusetts. If anybody wants to see where that is. I've never been to this one. But let's see, let me do maps instead. Here we go. So what do you think? There's a hydroelectric over here, but if you look over here, here's this reservoir. So I would imagine inside here is the actual pump storage facility, which again is completely separate. And this is the hydroelectric dam, so that's different. The pump storage facility, I'm guessing, is someplace in here. But like I said, I've never been inside this one, so I can't tell you. I mean, it might be over here. I don't see an inlet. I can't tell where exactly it is, but that's that facility. And that's an AC elementary or a 3-line diagram. They call it 3-line, but now people are calling it AC elementaries because It's elementary, right? It's the basic. That's where the term comes from. And it's AC because it's the alternating current basic drawing. This is literally how you wire up the AC part. Not the DC. Sometimes you show DC in here, but not. This one you actually don't even see. It doesn't even show you the field winding. So remember how I said the AC winding? You don't see any DC here. So the rotating field over here is shown in a separate drawing. Sometimes I show a little dashed line to show it going in here, but this one you don't actually see it. Questions? Is this TMI? Am I confusing you by trying to bring in a lot of real world stuff or a couple of nods? Yes. I won't test you on this part, but this is just hopefully get you ready for industry. But these are the type of things that as a proud person who's scored an A in this class, you can walk into your first job and say, I know this stuff. I've seen it all in class. Give me the hardest project you have. And if I fail at it, you don't have to pay me. I'll pay you money. But if I do well, donate this amount of money to EET program, right? What's that? Yeah. I'm not kidding about the ET. If you want to take donations, I'm sure the foundation will be happy to take it. Just don't put in my name. I want nothing to do with it. I can't get in trouble if it doesn't come to me. So. All right, I jest. I should stop before I get in trouble, right? Questions? All right, no questions. Have a great weekend, and I will see you all Monday. We've already got lab posted. Lab number 4, I think. So single phase transformers. We're way behind because we lost 2 weeks. We would have already had those 2 weeks before the test, but we still want to do some practical applications of transformers. That's why we're going back. So have a great
Thanks,
day.
Paul. Enjoy the rest of your day.
Take care.
You too. Have a good day.